So welcome to Unit 8 of Class 12 Physics, Atoms and Nuclei, and we will be starting with the 12th chapter, Atoms, and today is the first class for the atoms. So the term atoms, okay, or atom, it is actually the smallest known fundamental unit. Okay, now there are a lot of other, particles that we know which are, which we can break down an atom into. Okay, but previously, atom was the smallest particle of a chemical element that could exist. Okay, so now we know that atom includes nucleus, which includes protons and neutrons, and it is surrounded by the cloud of electrons. Okay, but before this model came into picture, there were a few other, models which was there, and we will first see two of the models which had come into the picture. Okay. So the first one we will be dealing with is the plum pudding model. Okay, so if you know how a plum cake looks, okay, so plum cake is a very like a dense cake, and there are a lot of different fruit elements, tutti frutti and raisins and everything. Okay, they are there, and they are all just just it looks like they have been scattered and they are put into the cake, and the cake itself is like a dense uniform compound. Okay, so this was actually given by J.J. Thomson in the year 1898. Okay, so J.J. Thomson actually gave this model, and according to this model, okay, so what J.J. Thomson said, that positive charge, okay, is the this entire region, okay, this entire atom is actually uniformly positively charged. Okay, so this is what Thomson suggested, that the entire volume, okay, the positive charge of the atom is just distributed uniformly throughout the volume of the atom. Okay, and the negatively charged electrons are actually placed in that volume. Okay, and negatively charged electrons are scattered. Okay, like we said in a plum cake, how the fruits and the raisins and everything is, it appears to be scattered in the plum cake or plum pudding. Okay, so this is a similar analogy that we see. So that is why this is called the plum pudding model. Okay, but later on, due to various experiments that were done with other other physicists, other scientists, we saw that this is actually not true. Okay, so this model, this plum pudding model, was actually then later on discarded. Okay, later discarded. So then we come to Rutherford's nuclear model of atom. Okay, so how did this come into picture was that Ernst Rutherford, okay, so this was given by Ernst Rutherford, okay, and he was actually, the former student of J. Thomson himself, okay. So he was the one who actually gave forward this nuclear model of atom. Okay, where he suggested that the entire positive charge that is shown by the atom and most of the mass of the atom is actually concentrated in a smaller volume. Okay, that is called a nucleus. Okay, so he said positive charge and most of the atom's mass is concentrated in the nucleus. Okay, so this is the nucleus. Okay, so this is what Rutherford said, and he said that the electrons are actually revolving uh, around this nucleus, like how planets revolve around sun. Okay, so he also suggested that electrons revolve around the nucleus. Okay, so this is what, this was what was given by as the nuclear model of atom by Rutherford. Okay, so usually, actually, Rutherford's, understanding of the nuclear model of the atom actually was the step forward to what we actually consider as today's atoms model. Okay, so it could not, there were some disadvantages to this model. Okay, so one of them was that it could not explain how atoms emit light. Okay, but or like at different wavelengths. Okay, at certain wavelengths only, and also that how an atom as simple as hydrogen, which only consists of, as you know, one proton and one electron, it has no neutron. Okay, it could later on we saw that there were experiments conducted and hydrogen itself could emit a very complex spectrum at different wavelengths. Okay, so uh, it surely gives us the distinction that in an atom the electrons revolve around the nucleus. Okay, but there were certain other things that needed to be explained. Okay, so which was done later on with experiments and further modifications to the atomic model. Okay, so what happened was in 1911. Okay, so in 1911, H. Geiger and E. Martin, okay, so these were two, uh, they actually, I think, worked with actually Rutherford, okay, and after Rutherford's suggestion, okay, so these two scientists actually performed few experiments. So what their experiments actually was called was the alpha particle scattering, the experiment. Okay, so this is actually the scattering experiment. Okay, so this was the setup where a beam of 5.5 mega evolts, okay, alpha particles were emitted from a 214 bismuth radioactive source. Okay, and the beam was directed towards a thin metal foil which was made up of gold. Okay, we'll see later how how the thin gold foil actually kind of affects this. Okay, so this was the setup, and this is the schematic. Okay, this is the schematic of the experiment. This is the schematic of the experiment. Okay, so this shows the working principle, or the working kind of setup of the entire experiment. So as you can see, this is the source of alpha particles. So this is your bismuth 21483. Okay, so this is a source, and the lead bricks are kept over here, so you can kind of direct these alpha particles in a narrow beam. Okay, so if you don't use the bricks, obviously it's going to be a scattered source already, but we need a directed, a sharp, narrow beam. Okay, so after crossing through these lead bricks, it comes out as a beam of alpha particles. Okay, now this thin line that you see over here, okay, this is actually the thin gold foil. Okay, so you can see that this beam of alpha particles is actually going to be incident on the thin gold foil. Okay, and as you can see, the thickness of it is very, very thin. It is 2.1 into 10 to minus 7 meters. Okay, this is very, very thin. Okay, so now once the beam is incident on the thin gold foil, okay, some of them are scattered back Okay, and some of them pass through it. There are very few which go, which follow the same path as the beam was, following, and a lot of them are actually scattered from the normal path at an angle. Okay, and these, the scattered particles, they are actually again they are directed towards a rotatable detector, okay, which consists of zinc sulfide screen and a microscope. So the microscope is actually used to, see the scattered particles. Okay. So what happens is when once they are scattered, okay, so these alpha particles actually produce light flashes. Okay, so they are like flickering, very tiny and very short time, flickering. Okay, so they are seen through the microscope, and the distribution of these scattered particles, okay, are actually studied as a function of the angle of the scattering. You can see theta over here. So theta is the angle of scattering. Okay, so the ones which are going straight have a very small angle of scattering. Okay, so fossa. So this was the entire kind of a setup, and how, the experiment was carried out and how the particles were detected after they were getting scattered. You can see that some of them actually backscatter. Okay, so but this is a very small fraction. Okay, so mostly they were kind of detecting the ones which passed through the gold foil and then scatter. Okay, so after the experiment was conducted, so a graph was plotted, okay, between the number of scattered particles detected with the scattering angle, okay. So over here you can see that a large number of, scattered particles are actually, have a very small scattering angle, okay. And the back scattered ones, okay, that is 180, okay. So like it is incident. If this is probably the thin foil, okay, so it is incident and then it is getting backscattered. So actually theta is equal to 180 degrees or pi. Okay, so this is a very small number over here. Okay, so this is 180, between 160 to 180. So the dots actually represent the data points, and the solid curve is the theoretical prediction, okay, based on the assumption that the target atom, this is actually done on the assumption of the Rutherford's model. Okay, so that what we had said, that the atom has small, dense, positively charged nucleus. Okay, so we assume this experiment was done with the assumption based on the Rutherford's model. Okay, so as you can see, many of the alpha particles actually pass through the foil. You can see the data points. Okay, a number of them are actually crossing the foil. Okay, and that is, they do not suffer any collisions. They just, pass through. Okay, so obviously there is going to be an angle of the theta scattering angle associated. Okay, and the point or the phenomena that actually kind of, confirmed Rutherford's model was that whenever an alpha particle is actually, getting backscattered, okay, so for that it needs to have a very large repulsive force in play. Okay, so this repulsive force, the only way that this can be, given to the particle to get backscattered is if the greater part of the mass of the atom and its positive charge were concentrated tightly at its center. Okay, so concentrated tightly at its center is again Rutherford's model. Okay, so where this is your nucleus, this is positively charged. Okay, and most of the mass is, concentrated in this nucleus, and there are, electrons around it. Okay, so there is a lot of empty space and most of the mass is concentrated in this. Okay, mass is concentrated in nucleus. Okay, so this is again validating the backscattering. Okay, the backscattering phenomena or the deflection of the alpha particle backwards is actually validating the Rutherford's model. Rutherford model. Okay, so this is what, this is what the experiment done by Giger and Madsen actually, kind of proved the understanding or the principle of the Rutherford's nuclear model. Okay, so that is why we can say that the Rutherford's nuclear model actually is, kind of, it is valid with respect to this experiment. Okay, so this is the model is Rutherford's model. Okay, is valid as per the experiment. Okay, so what was then, kind of, there were some of the takeaways from this experiment and from Rutherford's model. Okay, so Rutherford's experiment suggested the size of the nucleus would be about 10 raised to minus 15 to 10 raised to minus 14 meter. Okay, so it's small. Okay, but it could be quantified. And from kinetic theory, the size of the atom was around 10 raised to minus 10 meter. Okay. So what does this mean is that the size of atom is 10,000 to 100,000 times of the nucleus. Okay. So that means the atom is much, much larger compared to the nucleus. Okay, and the electrons in that sense would have also a large distance, okay, between the nucleus and the from the nucleus. Okay, so the electrons could be actually at a distance of, according to this, electrons are at a distance from the nucleus at about this is similar, so 10,000 to 100,000 times the size of the nucleus. Okay, so this kind of gives you the understanding of actually, how the size of the atom is compared to the size of the nucleus. Okay, so then we can say that the atom actually has a lot of large empty space. Okay, and if the atom has a large, has so much of empty space, there are chances that some of the alpha particles that were crossing through the thin gold foil, okay, would pass right through the thin foil because there is so much of empty space within each atom. Okay, but whenever the alpha particles actually, come near a nucleus, the intense electric field that is there, okay, because of that, because of the, the different charges of the electrons and the nucleus itself, because of this electric field, it scatters through a large angle. Okay, and the atomic electrons, since they are so light, okay, so they are not affected by the alpha particles that are passing through the thin metal foil that we were considering. Okay, so we can then also kind of prove this. Okay, we can also understand this. Okay, that we already said that since the thin gold foil is very thin, okay, the alpha particles are not going to suffer, kind of, continuous scattering or multiple scattering during their passage. Okay, so some of them will get scattered, obviously, but the most of them will just pass through. Okay, so we can, it is just, it is possible to understand the trajectory of such alpha particles, okay, which are getting scattered by a single nucleus. Okay, so how do we understand that? Is that alpha particles are actually, nuclei of helium atoms. So helium atoms, you have He, okay, 4 2, okay. So it has two electrons. Okay, so it has two electrons and it has two protons in it. Okay, so protons and electrons are equal in number, and it also has two neutrons. Okay, so that is why your atomic number is 4. Okay, so Suppose this is what we are considering as the alpha particle. So He4 is actually alpha. Okay, so this is your alpha particle that is actually, we are using the beam of alpha particles that we are using. Okay, so this is actually 2 units. So we are going to consider it as 2e. Okay, so where actually, 4 is the atomic mass number. This is 2 is the atomic number. Okay, so A and Z. Okay, because this is your say your element that we're considering. Z is your atomic number. A is your atomic mass number. Okay. So we are going to consider 2 units of positive charge for the alpha particle. Okay, so we are considering it as 2e. Okay. Now, when we consider the gold nucleus, okay, so for gold, okay, so your Z is equals to 79. Okay, and the charge will be, okay, so charge is Z E. Okay, so this is what we're so we can see that the gold nucleus, okay, or nucleus of gold is actually 50 times 50 times of alpha particle. Okay, so this is what we are saying. So then we can assume that the gold nucleus actually remains stationary throughout the scattering process. Okay, and if we assume, okay, so this is what we are assuming. Assumption is gold nucleus stays stationary. Okay, so it stays stationary throughout the scattering process. So if we are assuming this, then we can, try to understand the trajectory of an alpha particle. Okay, and it could be computed using both Newton's second law of motion and the Coulomb's law for electrostatic force of repulsion. Since we said that there is a intense electric field around the nucleus of the the gold, the thin metal foil, whichever we are using. Okay, so there is going to be a force of repulsion which would be in place. So that would be equivalent to the electrostatic force. Okay, so the magnitude of this, magnitude of the force can be given as F is equals to 1 by 4 pi epsilon 0 2e. Okay, this is the charge of the, if you remember the electrostatic forces, 1 by 4 pi epsilon 0 q1 q2 upon r square. Okay, r square is like the distance between them. Okay, so one of the charge of the alpha particle is 2e and the charge of the gold particle is ze. Okay, and r square, where r we are going to consider as the distance between alpha particle and the nucleus. Okay, and the force is going to be directed along the line that is joining the alpha particle and the nucleus. Okay, so if this is your alpha particle and this is your nucleus, okay, so the force is going to be on this. Okay, the magnitude and the direction of the force on such alpha particles is actually going to vary, okay, as it approaches the nucleus, and then it actually changes. Okay, so when it is getting, okay, so the direction and the magnitude is going to differ when it is coming towards the nucleus, and once it is getting back scattered, it will differ. Okay, it will change. So this is how, due to this Rutherford's understanding of the atom, as well as the experiment, the scattering experiment that was done, we could understand that there is a, there is kind of a force which is coming into play that is actually helping in the backscattering of such alpha nucleus. Okay, oh sorry, alpha particle. So now we'll see what is actually the trajectory that is kind of followed by the followed by the alpha particles when they are, scattered, or, or they are back scattered from the gold nucleus. You can see over here that this is your target nucleus. Okay. And these are all the different trajectories the alpha particle could take as and when, it is it is at a certain, it is coming with a certain velocity. Okay. And there is a certain angle, backscattering angle that is associated with this. Okay. So the trajectory that is traced by an alpha particle will depend on a parameter called the impact parameter. Okay. So that is actually given by B. You can see over here, this is the parameter. What is it? The impact parameter is actually the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. Okay, so this is the initial velocity vector. Okay, so you can see there are the kind of differ. Okay, so this is the perpendicular distance between the velocity vector and the center of the nucleus. Okay, so if suppose I'll just simplify. This is your target nucleus. Okay, and your this is coming like this. Okay, so if you draw a line from here, okay, the distance, a perpendicular distance between this initial velocity vector and the center of the nucleus is going to be B. Okay, so the B is actually going to change as per the kind of the velocity vector of the alpha particles. Okay, so suppose you are again, taking a beam of alpha particles, and you are, you are kind of, letting it, fall onto, say, target nucleus or the thin gold foil that we are, we had taken in that experiment. So the beam will get scattered in various directions. Okay, and over here now we are only considering one target nucleus and a beam of alpha particles. Okay. So then you can see that the alpha particles that are, closer to the nucleus, okay, will have very small b. Okay, so you can see this is very small. This, if we are considering, only this alpha particle, okay, so the b is going to be very small. If you consider this, the b is, it's increasing in quantity or in magnitude. Okay, so we can say that if you have small, say, r, okay, so if you are closer to the nucleus or the center of the nucleus actually, okay, so closer to the nucleus, okay, will have smaller b. Okay, will have smaller b, that is, it will have, kind of, the distance is very small. So it will have the scattering, or theta is going to increase. Okay, so you can see that when your B is almost, is equals to 0, your theta is, kind of 180 degrees. So this is like the maximum scattering. Okay, so maximum scattering is happening. Okay, so this you can see from the diagram itself. So the one that is, very close to the nucleus, okay, in distance, in that sense, okay, this beam is closer to the nucleus than, say, this one, okay, this alpha particle. So you can see that the scattering is kind of, total back scattering is happening. So your theta is almost, equal to 180 degrees. Okay, if your R is increasing, then obviously your B is going to increase and your theta is going to decrease. Okay, so say over here, okay, this one, this B is, very, very large. Okay, and you can see that it actually experiences no scattering and it goes through the, it goes undeviated, unaltered, unscattered. Okay, so if B is much, much greater than, say, B0, if we consider this as B0, okay, if we consider this as B0, okay, so your theta or scattering angle is actually going to be 0. That is, it will go undeviated, undeviated through the thin foil. Okay, through the thin foil. Okay, so with this we can see that only a small fraction of number of the incident alpha particles are actually going to get rebounded back. Okay, so rebounded back as in the back scattering. So actually you can say very small number of alpha particles experience head-on collision. Okay, the ones which are actually scattered very much. Okay, the theta is very high. The ones which for that, okay, they are actually very small in quantity. Okay, very small in number. So this will imply that the mass and the positive charge of the atom is actually concentrated in a very small volume. Okay, so if this is your target nucleus, okay, and since we know that it is surrounded by a space and there are negative electrons in it, so you can see that any B, okay, if your B is increasing, then it is actually passing through the atom. Okay, so it is not getting rebounded back. It is not getting it is not colliding with the nucleus. Okay, so this actually verifies or validates the understanding that all the mass or maximum mass of the atom is actually concentrated in the nucleus. Okay, so this we can also say is that the Rutherford scattering can be used to find the upper limit of size of the atom, size of the nucleus. Okay, we can understand till where the nucleus is actually extended. Okay, so wherever you will still find smaller theta or smaller angular scattering, actually till there only we can say that the nucleus is extending, and the rest of the space is actually the empty space which is having the cloud of electrons. Okay, then we will see that we now understood about the central part of the atom, okay, where we were talking about the nucleus, which has protons and neutrons. Okay, so now we'll understand how the electrons actually are, placed, or what is the trajectory, or what is the, kind of position of them in the atom. Okay, so we are considering very classical concepts, okay, in the nuclear model of Rutherford, given by Rutherford, okay, and it is actually giving us the understanding that the atom is an electrically neutral sphere, okay, consisting of a very small, massive, and positively charged nucleus at the center, and it is surrounded by a cloud of electrons, where the electrons are actually revolving in their respective stable orbits. Okay, so what is the final understanding of the Rutherford's nuclear modulus? Okay, so you have the central nucleus, okay, located, and there are these stable orbits, okay, around the nucleus. Okay, this is the ones, okay, and the electrons are revolving around the nucleus, okay, in certain stable orbits, okay, so they are all revolving around the nucleus. Okay, so this is the understanding of the Rutherford's nuclear model. Now obviously has to be some kind of a force, okay, that is keeping the electrons in these certain orbits. So we can give the expression of this by as the electrostatic force of attraction, okay, Fe, and this is going to exist between the revolving electrons and the nucleus. Okay, and this force is actually going to provide the centripetal force that is required to keep them in these stable orbits. Okay, so if we consider a hydrogen atom, okay, so we are going to consider a hydrogen atom or hydrogen atom. Okay, So for that, obviously, as we said, the force of electrostatic attraction has to be equal to the centripetal force. Okay, so that is going to give us 1 by 4 pi epsilon 0. Okay, E square, because we are going to consider the charge. Okay, E square is equals to mv square by r. Okay, disregard this diagram over here. This diagram is not useful. I will remove this when I'm giving the notes. Okay, so over here you can find the orbital radius. Okay, so r is going to be equal to e square by 4 pi epsilon 0 and v square. Okay, so we found the orbit radius of the electron. Okay, this is the orbit radius. Okay, now we will try to see the kinetic energy and the electrostatic potential energy of such an electron in the hydrogen atom. Okay, so you take kinetic energy. Okay, so K is going to be half mv square. Okay, so that is going to be equal to v square by 8 pi epsilon 0 r. Okay, and the potential energy can be given as potential energy U is going to be minus E square upon 4 pi epsilon 0 r. Okay, so what does this negative sign denote? Okay, negative sign shows that the electrostatic force is in the negative r direction. Okay, so if you then want to find the total energy of the electron of in such a hydrogen atom, so will be total E. Okay, so total E is the energy. Okay, is equals to K plus U. Okay, so that is going to be E square by 8, 8 pi, 8 pi, okay, epsilon 0 r. Okay, this is actually E. Okay, minus E square by 4 pi epsilon 0 r. So ultimately what you're going to get is minus E square upon 8 pi epsilon 0 r. Okay, so the total energy of the electron, okay, okay, this is for in a hydrogen atom. Okay, so it is negative. The total energy is negative. Okay, and this means electron is bound to the nucleus. Okay, so that is why you have a force of attraction between the electron and the nucleus. Okay, and it is going to be, so the electrons are actually bound to the nucleus. If your E was positive, okay, if your total energy was positive, this would imply that the electron does not have a closed orbit around the nucleus. Okay, so since it is negative, again, this is validating Rutherford's nuclear model. Okay, so where we said that the electrons are actually revolving around the centrally positive nucleus, okay, in stable orbits. Okay, so this is another validation of the nuclear model given by Rutherford. Okay, now we go into atomic spectra. Okay, so what does atomic spectra actually imply? That when suppose an atomic gas or vapor are actually, it is being excited at low pressure. Okay, and this is usually done by passing a current through it. Okay, and the gas or the vapor actually emits radiation. Okay, and this radiated emission is going to show you a spectrum. Okay, which actually contains the signatures at certain specific wavelengths only. Okay, so and this spectrum actually is characteristic of each element. Okay, each element in the periodic table, every element actually has a characteristic spectrum of radiation. Okay, and so we can, study the spectrum and for the, different elements, and we can understand their atomic structure also. So such spectrum are actually called emission line spectrum. Okay, so these are called emission line spectrum. Okay, and these usually consist of bright lines on dark background. Okay, so suppose you are considering this. Okay, so actually this light blue would be your dark background, and these lines that are given over here would actually be the bright kind of the bright lines that we can see. Okay, this is actually for a hydrogen atom. See, hydrogen atom has a very simple atomic structure. Okay, so that is why we are first trying to see on a very simple model. Okay, later on, as you will see that every element, even very big elements, have very different atomic structures. Okay, so study of these line spectra will actually give you the kind of a blueprint or fingerprint of identification of different gases. Okay, so hydrogen itself is a gas. So when actually white light is, kind of passing through the passing through this gas. Okay, so we can analyze the transmitted light using instrument called spectrometer, and we can see these dark lines. Okay, and these dark lines will actually correspond, or will actually give you the wavelengths at which you can find the emission spectrum. Sorry, emission lines spectrum, okay, of that particular gas. Okay, so this actually is called the absorption spectrum of the gas. Absorption spectrum, why? Since there's a dark, there's a dark band existing at particular wavelengths. Okay, so at those wavelengths, it is absorbed. Okay, the light is absorbed at those wavelengths that is particular for that gas. Okay, so then we have, spectral series. Even like over here, you can see there is a Lyman series, there's a Balmer series, and there's a Paschen series. Okay, and as you can see, these are all different wavelengths. Now, usually the human eye is only, it works in the visible region.